Welcome everybody. My name is Jean-Michel Fortin from Université Laval and I'm very happy to present our paper called Instance Segmentation for Autonomous Log Grasping in Forestry Operations. Modern forestry operations mainly implies two machines. The harvester, whose job is to cut and delimb the trees before leaving them in fixed length piles on the ground. And the forwarder, who collects the piles of logs and transports them back to the nearest road. These machines are highly mechanized and efficient, but productivity has not improved since the 90s, and operators are getting hard to find. Forestry is late compared to other industries such as mining and agriculture in terms of automation. In an effort towards unmanned forest machines, this research is a first step to provide a perception system for autonomous forwarders. But the fact remains that the forests are a mess. As you can see from these images, to find and collect logs, you need to deal with the fact that they're cluttered, elongated, and randomly oriented objects. These are all cases where computer vision, even relying on deep learning, currently struggles, and they are all combined together. Moreover, they are often partly covered by branches, vegetation, or even snow, as these machines operate during the day, during the night, and even in the winter. Let's mention also that no datasets exist for log grasping. Considering these observations, the leading question of our research is the following. Is AI ready for forestry? We all know artificial intelligence has achieved amazing results in computer vision, but it is still under heavy development. In forestry, we're just starting to see applications for neural networks for tasks such as tree species identification, tree trunk detection, or terrain object localization. But for the specific and complex case of precise logs detection, it is still to prove that the current technology is enough. Which is why we assembled a first-of-its-kind dataset called TimberSeg 1.0. which consists of log piles in various environments, such as trailers, the roadside, the lumberyard, and the forest. These are most of the places where forwarders and woodloaders operate. The dataset contains 220 images with a total of 2,500 instances of densely annotated logs with segmentation masks, as shown by these images. Now, only the graspable logs are annotated, since the partly visible one will become visible as the pile is collected. The images were taken by placing dashcams inside real forwarders during forestry operations in Canada. Other images were taken manually in sawmills, lumberyards, and above freight trucks. And finally, complementary data was taken from YouTube videos to add diversity from the other parts of the world. From this dataset, we trained and compared three instance segmentation architectures. The first one is Mask RCNN, proposed by He and al. In 2017. Mask RCNN first extracts axis-aligned regions of interest from the feature maps of the image before applying convolutional neural networks to predict a class, a bounding box, and a segmentation mask from each region. Now, as you can see from the output, Mask RCNN struggles to predict reliable segmentation in the case of cluttered, elongated, and randomly oriented logs. This is because the predicted regions of interest encompass multiple logs at a time, making it hard to distinguish the instances. To demonstrate this, we slightly rotate the image so that the logs are horizontal and the network predictions are almost perfect. Now, one technique that is typically used to improve Mask RCNN's performance in similar contexts is to search for rotated regions of interest that can better encompass individual logs. The output image shows a clear improvement over vanilla Mask RCNN, but the bounding boxes are not tightly fitted around the logs, and 3 instead of 2 logs were detected. Very recently, Cheng and al. Proposed Mask2Former, a transformer-based architecture for instance segmentation. Mask2Former works directly on the pixel level, avoiding the burden of regions of interest. Vision Transformers also uses global information from the whole image, making it more adequate with large objects, such as these logs, which are perfectly segmented. Now, to convince ourselves of its capabilities, we applied random cutout to test images and obtained these surprising results. We can clearly see that Mask2Former was able to understand the geometry of log piles as it completed cutout logs correctly. Even better, it added 2 imaginary logs on top of the pile in a logical configuration. We will now analyze the 3 networks' prediction on real footage from dashcams installed in a forwarder. This is 3 times the same sequence, and all networks are trained on a TimberSeg 1.0 dataset. On the left, we see that MaskRCNN works fairly good on the horizontal logs, but struggles as soon as the forwarder makes a turn. On this top frame, most of the logs are not detected, whereas the other 2 networks have gotten them correctly. Now, if we look at rotated MaskRCNN more carefully, we notice that the logs flicker a lot between frames, showing the inconsistency of the method. On this freeze frame, we see that some dense piles are not even detected as logs at all. Mask2Former, on the other hand, demonstrates a high understanding of the scene and provides precise and stable detections. We don't see quite the flickering from the second method. On this image, notice how no logs are missed by the detector, highlighting its high recall. That being said, the detector is still imperfect. A common failure case occurs when 2 logs are superimposed perpendicularly. The 2 logs are predicted as 1 when rotated MaskRCNN correctly segmented them. Another failure case is caused by the high similarity between the logs and their background. Here, the rot has been predicted falsely as a log. Quantitatively, MaskRCNN achieves an AP50 of 36.10 and a recall of 28.60 on our dataset. Its rotated counterpart achieves 52.78 average precision and 36.95 recall. And finally, Mask2Former overperforms the latter by a large margin of more than 30% on AP50, achieving 84.28 and a similar improvement on recall. Now, if we come back to our initial question, is AI ready for forestry? Considering the impressive results of Mask2Former with a relatively small dataset, it's fair to say that it has potential, but the failure cases need to be accounted for. Let's change the question a bit. Is robotics ready for forestry? Let's take a look. What you'll see in this video is not in the paper. We're currently deploying our solution in a simplified setting at the FP Innovation Facility in Montreal, Canada. We place a single stereo camera on the stick of the crane and use its generated depth map to estimate the pose of each detected log. The overlaid prediction, shown on the top left corner, are generated from Mask2Former trained on the TimberSeg dataset. On the bottom left corner, we see a digital twin of the log picker, as well as a point cloud generated by the stereo camera and the detected logs as red cylinders. On the right side, we see a drone view of the automated crane. The only thing that the operator does in this video is to click on the log he wants to pick up, and then the crane does it all autonomously. So today we presented the first densely annotated dataset of log piles in various environments, called TimberSeg 1.0. We evaluated some instance segmentation neural networks and showed that Mask2Former seems fit for cluttered, elongated, and randomly oriented objects, such as logs. For future works, we could leverage the large quantity of acquired unlabeled data or use multi-frame detection approaches to improve the quality of the detections. Please note that our code and dataset are available online for further research. Thank you very much for listening.